So continuing on with chapter 12, now we're going to be looking at independent samples when we're going to be comparing two independent samples. Your book uses the Wilcoxon rank sum test for two independent samples, but there is an equivalent test known as the Mann-Whitney U test. Minitab does the Mann-Whitney U test, which is an equivalent test to the Wilcoxon rank sum test. So when you read about nonparametric tests for two independent samples, when you read about it in the lecture notes and you read about it in your Triola textbook, you're going to be reading about the Wilcoxon rank sum test. But when we go to use Minitab to do the procedures, we're going to be doing the Mann-Whitney U test. Now, nonparametric tests that use ranks of sample data for two independent populations, they are used to test the null hypothesis that the two independent samples come from populations with equal medians, and the alternative hypothesis is the claim that the two populations have different medians. The requirements are that these two independent samples were randomly selected, and each of the two samples has to have more than 10 values. But there is no requirement that the two populations have a normal distribution or any other particular distribution. The Minitab procedure for doing the Wilcoxon rank sum test is that we'll be doing the Mann-Whitney U test. So you're going to be entering in your values for the two sets of sample data into columns 1 and column 2. Then you select stat, select nonparametrics, select Mann-Whitney, enter in C1 as your first sample, and enter C2 as your second sample. Then select the appropriate alternative hypothesis for your claim that you're testing, and click OK, and you will get some results. Now, the best way to read these results is to look at an example. So in your Minitab lab book, under Mann-Whitney and Kruskal-Wallis rank sum test, we're going to be, there's a set of BMI measurements of men versus women. So go ahead and enter in the 13 values of the male BMIs into column 1, and there are 12 values of female BMIs, enter them into column 2. Now we're going to be testing the claim that the BMIs for men and women are different. Thus, we're going to be selecting an alternative hypothesis that is not equal. When you click OK, you're going to get results. So let's look at how to interpret those results. The results tell us that the median BMI for men was 24.6, and the median BMI for females was 22.9. Our test statistic, our Mann-Whitney test statistic, is a W. It's equal to 187. If we wanted to do a 95% confidence interval at the same time, we would have seen that the confidence interval went from negative 2.300 to 4.897. Let's notice in here, 0 is included in this interval, which would tell us that we should fail to reject the null hypothesis. 0 is a possible value. Also, our p-value is 0.3412, which is certainly greater than 0.05. Thus, we come to the same conclusion by testing this using the Mann-Whitney test, or using the hypothesis test, or using a confidence interval. In either way, we fail to reject the null hypothesis. There is not enough evidence to suggest there's a difference between the BMIs of males and females. I want to point out that our samples were really fairly small, 13 men and 12 women. In reality, if our sample had been larger, in population, the median BMI of men is usually less than the median BMI of women. This test, because our samples were small, we did not get that conclusion. But if our samples had been larger, I believe we would have gotten that there was a difference. Now, if you remember in chapter 11, we looked at the ANOVA test if we wanted to test 3 or more independent samples. The nonparametric version of the ANOVA test is known as the Kruskal-Wallis test, which is also sometimes called the H test. It is a non-parametric test that uses the rank of the sample data for 3 or more independent populations. It's used to test the null hypothesis that the independent samples come from populations with equal medians versus an alternative hypothesis which claims that at least one of the medians is different from the others. But just like in the ANOVA test, it does not tell us which median is different, just that if we reject the null hypothesis, that one of them is not the same as the others. All right, so what are the requirements? We have to have at least 3 independent samples. All the samples had to be randomly selected, and each sample has to have at least 5 observations. But again, there is no requirement for normality or any other particular distribution. The Minitab procedure will enter all the values now. This is similar to what we did with the ANOVA test, the two-way ANOVA, where we entered all our values into one column. Then we enter our identifiers into another column where column 1, row 1 is a value. Column 2, row 1 is the identifier for that value. Then we select stat, select nonparametrics, select Kruskal-Wallis. We enter all the values into the responses and we enter our identifiers into factors and click OK. This is easier to see if we do an example. So we're going to use the data from the weights of poplar trees in the lab book. We saw, I believe this is the same data set that we did when we did lab 12 and we did the ANOVA, the one-way ANOVA. But you'll find this set of data also in the lab book in lab 13, where we did, under the section for Kruskal-Wallis. So there are 4 sets of 5 data values each. We want to enter all of 20 of those values into column 1. Then in column 2, you're going to enter in the identifier that goes with that value. Let's enter 1 to be for the 5 values, next to the 5 values that had no treatment. Enter 2 for the 5 values that had fertilizer as the treatment. Enter 3 next to the 5 values that did irrigation as the treatment, and enter 4 as the for the fertilizer and irrigation. Remember, column 1 values and column 2 identifiers must be paired next to each other. Then go to Stat, Nonparametrics, Kruskal-Wallis. Select C1 to go into the responses and select C2 to be our factors, then click OK. Let's see how we should interpret those results. Our test statistic is an H statistic and it's equal to 8.21. Our p-value in this case is 0.042, which is certainly less than or equal to 0.05. Thus our decision is to reject the null hypothesis, and our conclusion is there is enough evidence to say at least one of those medians is different than the others. Remember, we don't know whether treatment 1, treatment 2, treatment 3, treatment 4 are different. Maybe all 4 are different from each other, but we know that at least one of them is different. And in that case, then we would have to if we wanted to know which one was different, we would have to continue on with some more testing and do some pairwise testing. But we're not covering that in this class. In the lecture notes and in your reading, you saw that we also could use, there's a non-parametric version to the linear correlation that we saw in chapter 9. We won't be doing that in this course, but if you ever need to later on in your biology careers, you can read about it in the lecture notes that I have provided on the portal, or you can read about it in your textbook. All right, that is the end of the entire term. We have now finished all lectures, so go try some of the problems from chapter 12 and do Minitab Lab 13.